Hello everyone, welcome to this lecture series. Today we are going to start with integral calculus and we are going to learn about definite integrals and calculating them using Riemann sums, and we'll also talk about mean value theorem and fundamental theorem of integral calculus and how we can calculate the area between curves. Okay, so first to start with the Riemann sums, we need a few definitions before that. Okay, and the first definition that we need is the partition of an interval AB. Okay, so consider a closed interval AB. Okay, uh, the set P, which is an ordered set of numbers x0, x1, x2, so on xn minus 1, xn. Okay, so that the first number x0 is equal to a and the last xn is equal to b. Okay, and they are ordered, that means x0 is less than x1 is less than x2 and so on is less than xn. Okay, so this ordered set P of numbers is called the partition of AB. Okay, so what we mean here is that if you are given an interval from point A to point B, then we can divide this interval, okay, into a number of sub intervals by choosing points x0 as the lower end point and xn as the upper end point, and x1, x2, so on, the points in between these intervals. Okay, and you can easily see that this points x0, x1, x2, so on xn, it divides this interval AB into a smaller sub intervals. Okay, so the partition P divides the interval AB into n closed sub intervals, and these are the sub intervals x0 up to x1. So that's first sub interval, then x1 to x2, then x2 to x3, and so on xk minus 1 to xk, and so on xn minus 1 to xn. Okay, so we get exactly n sub intervals by using this partition. And you can also see that the union of all these sub intervals, okay, union of x0 x1 interval with x1 x2 and so on xn minus 1 to xn, if we take the union of all these sub intervals, it will be the original interval AB. The second point to note here is that the width of each subinterval we can calculate, and we denote the width of subinterval x0 x1 as delta of x1. Similarly, the subinterval x1 x2, its width is denoted by delta x2. So on the subinterval xk minus 1 to xk, its width is denoted by delta xk, and so xn minus 1 xn, its width is denoted by delta xn. Okay, and the partition can be done in any way, based on where the points are, these subinterval widths can vary, and if we choose the partition to be such that the subinterval widths are same. Okay, so that means each delta x, if we delta xi, if we choose to be equal delta x1 equals delta x2 equals delta xk equals delta xn, then you can easily see that they are n in number. So their sum will be n times delta x, which will be equal to the total width from a to b, which is b minus a. Okay, so if all n subintervals have equal width, then the common width delta x is equal to b minus a by n, because the total width is b minus a, which will be equal to n times delta x. Okay, so delta x can be easily written as b minus a by n. The second definition that we need is the norm of a partition. Okay, so the norm of a partition P, written as norm P. Okay, P in uh, between these vertical lines, two vertical lines on each side, and this notation we call norm of P, okay, is defined to be largest of all the subinterval widths, okay. So that means if there is a partition, we can calculate the subinterval widths of those partitions, uh, and the width of the largest subinterval will be equal to or denoted by this symbol norm of the partition, okay. So if norm p is a small number, then all of the subintervals in the partition p have small width, okay, because norm p denotes the largest width of this subinterval, okay. So if it is a small number, then all subintervals will be small, okay. So for example, say if you are given this set P, which is a partition of interval 0 to 2, by using the points 0.2, 0.61, 1.5, okay. So uh, we can easily see what are the subintervals present here, okay. The first subinterval will be 0 to zero point 0.2, the second subinterval is 0.2 to 0.6, third is 0.6 to 1, then fourth is 1 to 1.5, and last is 1.5 to 2, okay. So there are five subintervals these, okay, and so we can easily calculate the width of each, okay. And the first subinterval has a width of 0.2, the second subinterval has a width of 0.4, this minus this, okay. The third has a width of 1 minus 0.6, which is again 0.4. The fourth has zero point 0.5, and fifth also has 0.5, okay. So we can calculate the length of each subinterval, and by definition norm means the largest of all subinterval widths. So we can easily see that 0.5 is the largest value here. So norm of P is nothing but 0.5, the largest subinterval width, okay. Now once we know this, now we can define what we mean by Riemann sum, okay. So consider an arbitrary bounded function f defined on a closed interval ab, okay. So let this blue be a function f which is defined from a point a to a point b, okay. So from f of a to f of b, okay. The function may have positive as well as negative values. So you can see that at some points the function takes negative values, and on some points it takes positive value, okay. So this is just a general curve. One can also have any other form of curve, okay. uh, First we take the partition, okay. So consider a partition P of AB, okay. So let there is a partition from A to B by taking points x0, x1, x2, xk minus 1, xk, xn minus 1, and xn will be equal to B, so last point, and x0 equal to A, the first point, okay. So in each subinterval we select some point, okay. The point chosen is kth subinterval. In the kth subinterval, xk minus 1 xk is called ck, okay. So once we do the partition of this AB, so there will be subintervals x0 to x1 will be first subinterval, x1 to x2 will be second subinterval, and so on. We'll have subintervals. Now in each of the subintervals we choose one point. Say in the subinterval xk minus 1 to xk, in this subinterval we choose a point ck anywhere in this interval, okay. So in the first subinterval x0 to x1 we choose a point c1, in the second subinterval x1 x2 we choose a point c2, and so on. In the last subinterval xn minus 1 to xn we choose a point cn, okay. At the point chosen in each subinterval, we stand a vertical rectangle that stretches from x-axis to touch the curve at ck. Okay. So at the chosen point C1, we calculate the corresponding function value on the curve, which is C1 FC1. Okay, and with this height, we draw a rectangle of the width of the subinterval x0 to x1. Okay. Similarly, with the point C2, we see where is the function value, which is C2 FC2, and with this height, we draw a rectangle with the width which is delta x2, okay. Similarly, you can see with point ck we draw, see what where is the function value, and we draw a rectangle with the height fck and the width of this delta xk. Okay, and so on, continue this to the last subinterval for the chosen cn point. The corresponding point is cn fcn, and with this height of fcn we draw a rectangle with the width of delta xn. Okay, so here now we uh, calculate on each subinterval we calculate the product of this form fck times delta xk. Okay, so that means for this kth subinterval this the function value fck, okay, which will be this height multiplied with the delta xk, which is this length of the subinterval. Okay, so this height times this. Okay, so wherever this function is positive, okay, so this height times this width uh, is the area of this rectangle. Okay, so similarly if this is the fcn and this is delta xn, then this height multiplied with this width will be the area of this rectangle. Okay, and whenever the function value fck's are negative, then the product fck times delta xk, that means for example in the first case fc1 times delta x1 is a negative number, and the negative of the area of the rectangle of this first rectangle. Okay, so because this is height is in the negative direction. So if we calculate them in magnitude, so then if we calculate this in magnitude for each interval, then they are nothing but the areas of these rectangles. Okay, but we are not calculating magnitudes, but for the positive function side it will be uh, areas, and on the negative side it will be the negative of the areas. Okay, so clearly this fck delta xk, this product can take positive values, it can take negative values, or it can take zero value depending upon the sign of this fck. Okay, so this product is positive, negative, or zero depending on the sign of fck. Okay, so there is it is important to note here that we can take partition in with the points x0, x1, so on, anywhere. So there can be infinite number of different partitions possible for this interval a to b. Okay, and ck's are any points chosen in this subinterval. So it is possible to choose ck any point in this interval xk minus 1 to xk. So there are infinite many possibilities to choose ck's. Okay, so this product which we have formed depends on how the partition is taken, and also depends on how the point ck is chosen. Okay, so now if we add all these fck delta xk for each subinterval. Okay, so if we sum this up, then we can write this as summation k is equal to 1 to n of fck delta xk. So with k is equal to 1, it is for this first subinterval. For k2 it will be second, k3 third, and so on, nth subinterval. So if we add all these up, we denote it by sp, and this is called the sum is called the Riemann sum for f on the interval ab. Okay, so there are many such sums depending on the partition we choose. Okay, and the choices of points ck in the subinterval. So clearly you can see that any Riemann sum which is associated with a partition of a closed interval AB defines rectangles that approximate the region between the graph of a continuous function and the x-axis. So when the subinterval have equal width delta x, we can make subintervals, uh, these subintervals thinner by increasing n. Okay, so when n becomes large, that means the number of partitions increases, and if all delta the subintervals are of equal width, then when n grows large, delta x becomes small and small and small. Okay, but when the partition has subinterval of varying width, we can ensure that they are all thin, okay, these subintervals, by controlling the width of the widest of the subinterval. Okay, that is by making the norm of p as small as possible. Okay, so the partition with norm approaching 0 lead to collection of rectangles that approximate this region with increasingly accuracy. Okay, so clearly, if I increase the number of partitions, okay, you can see that the number of partitions are more than previous page, and here the number of partitions are further more than this what we have taken here. So clearly you can see that the region bounded by the curve and the region due to the uh, partitions, they are approximating each other when the number of partitions become large. Okay, if the width of the each subinterval is same, then just by increasing the partitions we can uh, approximate these two with each other. But if the widths are not same for each subinterval, then to make sure that the width of the partitions goes to 0, it is important to take the norm of p to be tending to 0. Okay, so clearly the graph with rectangles from finer partition of AB approximate the region between the graph of f and the x-axis with a very increasingly accuracy. Okay, so and this results in our definition of definite integrals, as you will see that when n if delta x are each of the widths are same, then simply we can take n tends to infinity on this. But if they are of different widths, then we can use the norm concept, that we can choose norm of p going to 0, which is same as uh, n tends to infinity, but it will make sure that the each subinterval becomes small. Okay, and that will lead to our next definition, which is the definite integral. Okay, so let fx be a function defined on a closed interval ab. We say that a number j is the definite integral of f over the interval ab, and that j is the limit of the Riemann sum, this if the following condition is satisfied. Okay, so if we are going to take the limit definition on here, and it's this definition says that the limit on Riemann sum is same as the definite integral of function over the interval AB. Okay, so given any epsilon positive, there is a corresponding number delta positive, such that for every partition that we choose x naught to xn of AB with the property that norm of P is less than delta, and any choice of ck in the subinterval xk minus 1 to xk, we have that the Riemann sum is sufficiently close to the number j, which is the definite integral of function. Okay, and how close it is, its difference is epsilon close. Okay, so the distance of j from this Riemann sum is within the epsilon distance whenever the norms are sufficiently small. okay, less than delta, okay. And if this is true for whatever partition of the interval we choose, and also uh, for every choice of the points in the subintervals, okay, then we say that j is equal to the limit n tends to infinity on this, or if subintervals are of different width, then j is equal to limit norm p tends to 0 on this Riemann sum, okay. So again, we have many choices of the partition P with norm going to 0, and many choices of CK for each sub interval of partition. The definite integral will exist when we always get the same limit j, okay. If we get this value as unique value, no matter what choices are made for the partition and for the points ck in the partition, okay. So then because the limit exists, we can write this definition that j will be limit on the Riemann sum, and limit is norm p going to 0, okay. Now norm p is the width of the largest subinterval. It will tend to 0 only when limit n tends to infinity, okay. So limit n tends to infinity and norm p tends to 0 will play a crucial role if the width of the subintervals are different based on partition, okay. And since we this was the symbol which we use for integral, so the symbol for the number j in the definition of definite integral is this, that it is uh, integral a to b fx dx, okay. So in this symbol here is the integral sign, and the integral varies from a to b. The a which is written below the integral sign is called the lower limit of integration, and the number which is written on the top of the integral sign is called the upper limit of integration. um, the function fx is the integrand, and the variable x is the variable of integration, okay. And we read it as integral of function fx dx, integration from a to b, okay. So because j is the value of this integral, so we can equate these two, and uh, when the condition in the definition is satisfied, we say that the Riemann sum of f converge to the definite integral j is equal to this, okay. So that means if this limit exists, then this limit of Riemann sum is nothing but the value of this integral uh, a to b fx dx, and that we say that the function is integrable over the interval a to b. Now this integrability of the function uh, depends on whether this limit exists or not, and not every function defined over the closed interval ab is integrable, even if the function is bounded, okay. That means the Riemann sums for some function may not converge to same limiting value or to any value at all, okay. But fortunately most functions that occur in applications are integrable. So for the integrability of function, there is one result which is important, that if a function f is continuous over the interval ab, or if function f has at most finite many jump discontinuities there, okay. So that means function is continuous except only at few points where it has jump type discontinuities, then the definite integral exists and function is integrable over f over the interval ab, okay. So whenever we have a continuous function or a piecewise continuous function, then the function is integrable over ab, okay. And if the function is integrable, that means the uh, limit of the Riemann sum will exist and it will be unique. So for such functions it will be easy to solve using Riemann sum. That means we can choose any one partition and we can take any one choice of ck points, and we can solve this to calculate the value of the integral if we need to apply the definition of Riemann sums. Okay. uh, there are few properties which we need to discuss, and first of them is the max mean inequality. Okay. So it says that the uh, integral of the function over the interval a to b is never smaller than the uh, minimum value of the function times the length of the interval, and the uh, and it is never larger than the maximum value of the function times length of interval. Okay, so clearly you can see that if function is integrable in AB and if function has a maximum value as max f, and it has a minimum value as min f on this interval AB, then the uh, integral of the function is always greater than equal to the mean f times the length of the interval, which is b minus a, and is always less than equal to the max of the function, its maximum value times the uh, length of the interval b minus a. Okay, so uh, graphically, if there is a curve y is equal to fx, so you can see that this is the minimum value of the function in this interval, so this is your min f, and here it is the maximum value of the function in interval AB, so you have a max f. So clearly the integral a to b fx dx, which is known to be the area between the curve and the x-axis. Okay, so this whole area is bigger than the this rectangle below min f, and is area over below the blue is less than the area of the rectangle max f. Okay, so this is your one result. Okay, similarly we have a few other properties which are important, and you can remember these properties, that if f and g are integrable over the interval AB, then the definite integrals satisfy these properties. And first is the order of integration. Okay, so far we said that we integrate over the interval a to b, but what if we integrate it backwards from b to a? Okay, so the integral b to a fx dx is nothing but minus of a to b fx dx. Okay, so the change of sign is due to the delta x changing in sign, because when we move from a to b we choose, say, delta x1 to be x1 minus x naught. Okay, then x2 minus x1. So if we move backwards, then delta x will be reversed. Okay, so the next delta xi in forward direction is minus of delta xi in the reverse direction. Okay, and the function value will remain same, fck's. Okay, so the Riemann sum will just change this sign due to delta xi. So b to a integral fx dx is minus of a to b fx dx. Okay. The second is the zero width interval. Okay, so that means integral of fx from a to a over a single point is 0. This is because the delta x size will be 0. So fck times delta xi will be 0. The Riemann sum is exactly 0 in this case for a point. Okay. Uh, the constant multiple rule, that the integral a to b of k times fx dx is k can take b, we can take outside the integral and write it as k times integral a to b fx dx. The fourth result is the sum and the difference rule. Okay, that the integral of sum of function or the integral of difference of function is sum of their individual integrals, or the difference of their individual integrals. So a to b fx plus gx dx is a to b fx dx plus a to b gx dx. Okay, the additivity property, that the integral over the intervals a to c here it should be fx, not gx. Okay, this is f function here. The integral from a to c fx dx is equal to a to b fx dx plus b to c fx dx if b is a point between a and c. Okay, so if you have interval a to c and b is a point inside, then integral from a to b plus integral from b to c will be same as the integral over the complete length a to c. Okay, so again remember, this is not gx, this is a fx function, same fx function. Okay, uh, the domination result, which says that if uh, fx is greater than equal to gx throughout the interval ab, then the integral of fx from a to b is also greater than equal to the integral over gx from a to b. Okay, so if function is bigger than gx curve, okay, for all points AB, then the corresponding integral over AB is also bigger than the corresponding integral of gx. Okay. And now we take one definition that now we can use it to calculate the area under the graph of non-negative function. Okay, so if you have y is equal to fx is a non-negative and integrable over a closed interval ab, then the area under the curve y is equal to fx over ab above the x-axis is the integral of function from a to b. Okay, and so the area under the curve y is equal to fx can be calculated as integral a to b fx dx. Okay, if y is equal to fx is a non-negative curve. Okay, so we take one example here. Say compute this integral 0 to b x dx and find the area a under the curve y is equal to x, because this y is equal to x is the integrand over the interval 0 to b positive. Okay, so clearly you can see that y is equal to x line from 0 to b with b positive is a curve above the x-axis, and so this 0 to b x dx, which is like a to b fx dx, this will compute the uh, area under this curve y is equal to x above the x-axis and below this curve. Okay, so you can see that this is the y is equal to x line, and interval is 0 to b. So when x is b, this height will be b, because y is b, so this point is b comma b here. Okay, so clearly by geometry you can see that this is a area of this triangle, which is half into base into height, and so you can see that the area is nothing but b square by 2. Okay, so we'll uh, calculate this integral using Riemann sum to show you how to use the definition of Riemann sum and how to use the limit on the Riemann sum to find this integral value. Okay, so given this 0 to b, we can take partitions x naught as 0 and xn as b, and the points x1 x2 x3 so on. Okay, and because y is equal to x uh, is a continuous function on 0 to b, so it does not matter how we choose the partition or what point ck we choose, as long as the points are chosen such that norm approaches 0. All choices will give exactly the same limit value. That's by the definition of integrability. So it is sufficient to choose one partition and one set of ck's, and calculating limit over the partial, this Riemann sum on that, to find the integral value. Okay, so let us choose the partition of equal width. Okay, and let us choose ck points. Okay, So we consider the partition P that divides the interval 0 to b into subintervals of equal widths delta x, and we know that it is b minus a by n, and in this case a is 0, so each subinterval will be of width b by n, and choose ck points in each subinterval as right endpoints. Okay, the partition of 0 to b with this width b by n, so partition will be this 0, then next will be b by n, 2b by n, 3b by n, and so on, nb by n, and we choose ck points to be the right end point of the subinterval. So first subinterval is 0 to b by n, its right point is b by n. Second subinterval is b by n to 2b by n, and its right point will be 2b by n. Okay, so and the last will be n minus 1b by n to nb by n, so end point will be nb by n. So that means the point ck in subinterval is kb by n. In the c1 will be in the first interval, which is b by n. C2, which is 2b by n, will be in the second subinterval, and so on. Okay. Now, if we calculate the function value ck times delta xk summation, which is the Riemann sum. Okay, so summation k is equal to 1 to n fck delta xk, and it is given that the curve is y is equal to x. That means fx is x. So f of ck is nothing but the point ck, which is kb by n. So fck is kb by n, and delta x is b by n, and so this product with summation k from 1 to n. Now so it is b square by n square can go outside the summation as a constant, and we will have summation of k. Okay, so it can be written as b square by n square summation k. So with k 1 2 so on, it is the sum of first n numbers, and so we know its sum is n into n plus 1 by 2. So we can just rewrite this as b square by 2 times 1 plus 1 by n. And when if we take limit norm p tends to 0, which is same as limit n tends to infinity on this, so you can easily see that this number will tend to b square by 2, and limit n tends to infinity on this will be equal to integral, which is nothing but b square by 2. Okay, so when n goes infinity or norm p goes 0, this results in b square by 2, which is limit on this, which is equal to the integral value. Okay, so by the definition of Riemann sum also, you can see that the integral 0 to bx dx is nothing but b square by 2. Okay, so that's one definition uh, example. Okay, so now we take talk about a few definitions here, like the mean value theorem for definite integrals, which says that the function can take its average value at least once in the interval AB. Okay, so it says that if f is continuous on the interval AB, then at some point C in AB, the function value at C is equal to the uh, average value of the uh, function. Okay, so this you can clearly see this is the definition of average value of the function. 1 by b minus a to b fx dx is nothing but the average value of the function, and it says that the average value of function must be taken by the function for at least one point c in the interval. Okay, so to prove this, you can use this min-max inequality. If we divide both sides of the max-min inequality by b minus a, we can see we just wrote max-min inequality, which was min f into b minus a less than integral less than max f into b minus a. So if we divide with b minus a, the max-min inequality will become this. Okay, and so it says that the minimum value of the function will be less than equal to the average value of the function will be less than equal to the max value of the function. Okay, and uh, since the function is continuous on the interval, by the intermediate value theorem for continuous functions that we studied during differential course, function must assume every value between the min f and the max f. Okay, so it must therefore assume the value this, the average value at some point C in the interval AB. Okay, that means f of C must be equal to this for at least one point C in this interval. Okay, so this is the mean value theorem for definite integrals. Okay, now we have the fundamental theorem for integral calculus, uh, and there are two parts. First is the existence of the antiderivative, and second part is the evaluation of the integral using the antiderivative. Okay, so because it is very difficult to compute the definite integrals by calculating the limits of the Riemann sums. Okay, so this theorem, okay, uh, the part 1 and part 2 in combination, they allow to compute the definite integrals using the antiderivatives. Okay, so the first part of the fundamental theorem of this integral calculus, it says that if you have a function which is continuous on the interval, then the integral a to x ft dt, we denote it by capital Fx function. This is also continuous on the interval and differentiable on the interval, and its derivative, the derivative of capital Fx, is nothing but the small fx function, the original function. Okay, and we can write that f dash x, which is derivative of fx or derivative of the integral, this is nothing but fx. Okay, so this theorem makes sure that there is a antiderivative fx, existence of this function fx, such that its derivative is the this small f function. Okay, so to prove this result, we know by definition of limit that the derivative of any function is limit h tends to 0 f of x plus h minus fx over h, where x and x plus h are any 2 points in the interior of this AB interval. Okay, uh, and since fx is this integral a to x ft dt, so we can substitute this here by f of x plus h will be a to x plus h ft dt, and fx is already there, so we can substitute the value of capital F of x plus h and f capital F of x. So it will be limit h tends to 0 1 by h of for capital F of x plus h, this integral will be a to x plus h ft dt minus capital Fx will be a to x ft dt. Okay? And so a to x plus h, often the integral minus a to x ft dt will be nothing but x to x plus h. Okay? So if there is a interval a to x plus h, then a to x plus x to x plus h will be the whole interval. That's the property we wrote. We had just few slides ago. So these two integral difference will be same as integral of x to x plus h ft dt. Okay, so limit h tends to 0 1 by h x x plus h ft dt. Now if we look at here, then this is, if this x is a, this is b, then this h is nothing but b minus a. Okay, x plus h minus x is h. Okay, so clearly this 1 by h times this integral is nothing but the average value of the function in the interval x to x plus h. And the mean value theorem, it says that if the function is continuous, which is given, okay, then there is at least one point C in the interval here, which is x to x plus h, such that the function at C takes on the average value. Okay, so we can utilize that concept here of mean value theorem, and so according to mean value theorem, there is at least one point C in x to x plus h, such that the function value of C must be equal to the average value. Okay, uh, and then if we take limit h tends to 0 on both sides. Okay, so when limit h goes to 0, then because C lies between x and x plus h, when h goes to 0, C must become x. Okay, So as h tends to 0, x plus h approaches x, and because c lies between these 2 points, so c also approaches x. So f dash x, which is limit of this, and so limit of this is limit on fc, and because function is continuous, so when c approaches x, fc approaches fx. Okay, so we have this result that the derivative of the function capital F is same as small f function. So that means that function this has the antiderivative, and because this is differentiable function now, so it also implies that this function is continuous on AB. Okay, and this was for any interior point, so one can prove for the endpoints by taking for the lower endpoint we can take limit from the positive side, and for the upper endpoint we can take limit from the negative side and prove the result. Okay, so this is your fundamental theorem, uh, part 1. Okay, the existence of antiderivative. The second fundamental theorem is to uh, calculate the integral using this antiderivative. Okay? So if f is a continuous function over AB, and capital F is the antiderivative of function f on AB, okay, and so this f is any antiderivative, any one antiderivative of this, then the integral a to b fx dx can be evaluated as the function capital F, which is the antiderivative, its value at the upper and lower limits of the integration. So f of b minus f of a. Okay. So if you know the antiderivative of this, we can evaluate this integral as the value of the antiderivative at the upper endpoint minus the lower endpoint. Okay. Uh, for the proof of this, the first fundamental theorem that we studied, the previous part 1, it says that there is a antiderivative of f. Okay, and say let this be an antiderivative gx, which is a to x ft dt. Okay, and since f is any antiderivative of this, so f must be a linear function of this g. Okay, so if f is any antiderivative of this f, then fx must be, this capital Fx must be equal to this plus c for some constant c, uh, for a less than x less than b in this interval. Okay, and this result we have already done in differential calculus. So if you have not, if you have if you do not remember, you can just go back to the previous uh, lectures in differential calculus where we prove that if you have two functions, then they will satisfy this relation. Okay, uh, so if we calculate this right hand side fb minus f of a, okay, and f of b will be gb plus c, f of a will be ga plus c, so we can substitute fb as gb plus c and fa as ga plus c, and so if we solve this it will be gb minus ga, and because gb from here we can calculate gb is a to b ft dt, and ga will be a to a ft dt. Okay, and because there is a property that integral over a point a to a is 0, so this second integral is exactly 0, and we are left with this integral a to b ft dt. Okay, so this proves our second fundamental theorem, that the integral of the function f from a to b is the where its value can be calculated by the value of the function's antiderivative at upper endpoint minus the function value at the lower endpoint. Okay, so this result. Okay, and this result, two results are now useful in the sense that we do not need to calculate the partitions and the points, and then develop a Riemann sum and take limit to find integral value. If you know that the function is continuous and you know the antiderivative, and in fact any antiderivative of the function, then you can calculate the integral value directly using this formula. Okay, so the last topic that we are going to take on today is finding area between the curves. So if you have two functions or curves f and g, are continuous with the property that fx is greater than gx throughout the interval ab, then the area of region between the curves uh, f curve and g curve from a to b is the integral of f minus g from a to b. That means the area between curve f and g, if f is always greater than g over the interval ab, is integral a to b of f minus g dx. Okay, so like if you have this blue curve as fx curve and g curve as this yellow curve, then because fx is always greater than gx for every point in the interval a to b, so the area between these two curves, this whole area, will be or can be calculated as integral from a to b of fx minus gx. Okay, so if we take the partition of this a to b, okay, by taking points x0, x1, x2, so on, and so if this is your kth subinterval, okay, with width delta x k, then and if we choose any point ck here, so you can see that this point will be ckf ck and the corresponding point here will be ckg ck. So if we calculate the this rectangle, it will be this height times delta xk, and this height is nothing but fck minus gck. Okay, so the this rectangle area will be fck minus gck into delta xk, and if similarly we calculate this for all uh, subintervals and add them to write the Riemann sum, and then take limit n tends to infinity or limit on norm p tends to 0, then immediately you see that because it is fck minus gck delta xk summation, so when limit goes to or norm goes to 0, it will be the integral, which is nothing but f minus g dx. Okay, so the similar concept of Riemann sum that we did can be applied here to prove this result for the area. Okay, and say we take one example here. Find the area of the region enclosed by the parabola and the line y is equal to minus x. Okay, so there is a curve y is equal to 2 minus x square, and there is a straight line y is equal to minus x, and we want to find the area enclosed by these two curves. Okay, so if you are given this curve here, this is a parabolic curve y is equal to 2 minus x square blue, and there is a straight line y is equal to minus x. So we want to find the area enclosed between these two lines, so we must find out the points of intersection so that we know what is the area enclosed. Okay, so we can equate these equations to find the points of intersection. That means 2 minus x square equals minus x. We can solve for x to find the points, which is x minus 1 and x value as 2, and then we can easily see from here what are the y values. So we can find these 2 points, minus 1 1 and 2 minus 2, uh, by the point of intersection of these two. And so if we have to find this, you can clearly see that between minus 1 to 2, which are the points of intersection, or which becomes the uh, length of the interval on the x for which this area is enclosed. So from minus 1 to 2, uh, everywhere the function curve fx is greater than the curve gx. Okay, so from here fx is greater than gx up to here. Okay, from minus 1 to 2. So these conditions are satisfied, and so we can calculate the area by this integral a to b fx minus gx dx. Now a and b are the lower points of x to upper point x, which is minus 1 to 2. So integral minus 1 to 2 fx minus gx. Fx is the upper curve, which is 2 minus x square, and gx is the lower curve, which is minus of x. So clearly the region runs from x is equal to minus 1 to x is equal to 2, and the area can be calculated by this formula because f is greater than g everywhere in this interval. and so we just need to integrate -1 to 2 minus x square plus x dx. Okay, and because we know the antiderivatives of this, okay, because x derivative is 1, so 1 antiderivative will be x square, so this will give 2 times x, this will give x square, will give x cubed by 3, x will give x square by 2, and we just need to plug the upper limit, because this is your capital F function, and second theorem says that we can calculate the integral value as capital F function value at b minus capital F function value at a. So we just need to put the upper value minus the lower value. Okay, so if you plug 2 value here, you will get this minus 1 value here. Okay, and then we can solve this to write that the area enclosed is 9 by 2. Okay, so take one more example here. Say find the area of the region in the first quadrant that is bounded above by y is equal to root x curve and below by the x-axis and the line y is equal to x minus 2. Okay, so we have to find the area of the region which is bounded above by this curve y is equal to root x. Okay, so area below this we have to find, and bounded below by the x-axis, which is y is equal to 0 line, and y is equal to x minus 2 line. So we have to find the area below this and above these two. Okay, so in the first quadrant, that means the area between which is lying here. Okay, this we have to find out. Okay, so now this curve is always greater than this curve and this curve. Okay, but at the bottom there are two different curves. Okay, so we can divide this whole area into two areas. One is here with the upper curve y is equal to root x and lower curve y 0, and the second area which is upper curve y is equal to root x and lower curve y is equal to x minus 2, and so this area plus this second area will be the total area that we want to calculate. Okay, so we can divide or find the area by calculating two integrals, integral from 0 to 2 of fx minus g1x, where g1 is y0, and plus the area of this region which is integral from 2 to 4 fx minus gx dx, where fx is root x and gx will be x minus 2. Okay, so let we call this curve as g1 y0 curve and call this curve as g2. Okay, the area will be uh, the integral fx minus g1x, so this curve minus this curve, up 0 up to 2, so this area will be calculated, and plus fx minus g2x, so this minus this, from 2 to 4, so this area will be calculated. Okay, so now we can easily substitute. Fx is root x and g1x is 0, so it's simply root x integral 0 to 2, and fx is again root x and g2 is x minus 2, the second curve. So we can integrate this, and a substitution of upper limit minus lower limit, we have the value of the area which is 10 by 3. Okay, so you can see that there's one curve above but two different curves at the bottom, so we have to divide the whole area into two areas, that means sum of two integrals. Okay, but this was when we integrated with respect to the variable x, but if we, instead of taking the partition on the x-axis, if we take the partitions on the y-axis, that means if we want to integrate this with respect to y by taking horizontal partitions, okay, then you see that there is only one curve, y is equal to x minus 2, which will be above this y is equal to root x. Okay, so we can say that we can calculate x in terms of y as x is equal to y plus 2, and from here x is equal to y square. So x is equal to y plus 2 is a curve which is always greater than x is equal to y square curve. So we can also use the area definition in terms of integral c to d of uh, function of y minus the other function of y dy. Okay, so like we can find the area between the curves by integrating with y variable, treating this as the uh, fy curve, and this is the gy curve. And because fy is always greater than gy from 0 up to this height, okay, so 0 to 2, so we can integrate from 0 to 2 the fy curve, this one, which is x is equal to y plus 2 minus x is equal to y square, okay. So y plus 2 is the upper curve and y square is the lower curve, their difference from 0 to 2. So if we integrate this, we will get the same area, okay. So this way it is easier to integrate than the vertical way with x, okay. So we can solve in with variable x, or we can also solve with the variable y, okay. So this was about the integral calculus of one variable, single integrals or finite integrals by using Riemann sum and the definition of fundamental theorem of calculus, okay. So we close this first lecture here, and in the next lecture we'll talk about applications of these definite integrals, okay. Till then, have a very good day.